Good day everyone and welcome to the second part of our video regarding heat transfer by conduction. In this video, we will be discussing unsteady states conduction. So let's begin. Under unsteady state conditions without heat generation, with heat transfer to only one direction, then we can simplify our general energy equation into the following equation. We have alpha or thermal diffusivity multiplied by the second derivative of temperature with respect to position x is equal to the partial derivative of temperature with respect to time. Now, our simplified energy equation is a true partial derivative equation because we have two independent variables, that is position and time. For these types of equations, we can solve this analytically using a Fourier series solution. But for this lesson, we will not be discussing the analytical solution because it gets complicated. Instead, we will be discussing a graphical solution for this problem. But before we go to that, let's first imagine what happens during the unsteady part of conduction. Consider a small sphere contained within a volume of fluid as shown in this figure. Assume that heat transfer through the sphere is rapid such that at any time t, the temperature in any point in the sphere is the same. What we mean by that is even though the heat transfer is unsteady state, meaning the temperature of your sphere varies with respect to time, it will not vary with position because the heat transfer is fast enough. We can express the temperature as a function of time as the following. This is the temperature at any time t at any point in the sphere minus the temperature of the surrounding fluid, we use T infinity, divided by T sub 0 or the initial temperature of the sphere minus T infinity. That is equal to e raised to negative HAT over rho CPV. Now this exponent is what we are interested in. If we arrange this exponent into this form, you can see that the exponent can be expressed in terms of two factors. We have HV over A over K times alpha T over V over A squared. Just take note that V here is the volume of the body and A is the surface area of the body that we are studying. Now we have rearranged the exponent into this form because each of these factors has its own significance in unsteady state heat transfer. The first one, HV over A over K, is called the BO number. And the second one, alpha T over V over A quantity squared, is called the Fourier number. That means that if we multiply the BO number and the Fourier number, and that becomes the exponent of E, then we have what we call the temperature profile of the body under unsteady conditions. You know that this transfer is unsteady because we have time as one of the variables of our temperature profile, meaning that the temperature is varying with respect to time. Let's talk a bit more about the BO number because the BO number is a very important dimensionless number in the study of unsteady state heat transfer. Again, the BO number can be computed by this expression H times V over A all over K, but technically the BO number is defined as 1 over K all over 1 over H times V over A. The 1 over K on the numerator is called the resistance to conduction, and the 1 over H times characteristic length on the denominator is called the resistance due to convection. So we are looking at the conduction of heat within the species as well as the convection of heat outside of the species. This involves a fluid outside of the species. Now, it is through the value of the BO number that we will be able to determine what type of solution will we adopt. We have two types of systems. We have what we call the lumped system and the distributed system. The lumped system is what we have earlier discussed. It is a system wherein the temperature is not varying with respect to position. It's only varying with respect to time. So therefore, if you have a lumped system, we can say that the temperature is a function of time only. Okay? Another way of saying that is if we have this spherical specimen, let's say for example our object is a sphere, and if we consider this as a lumped system, that means that at a certain time t, the temperature at the center of the sphere is just the same as the temperature at the surface or at any other point of the sphere. The opposite of that is called a distributed system. In the distributed system, the temperature is a function of both time and position, meaning at a certain time t, the temperature at the center of the sphere is different with the temperature at the other parts of the sphere. You can imagine how we can have a lumped and a distributed system. Let's say, for example, you have a very small sphere. It's more likely to be categorized as a lumped system because of its small size and its large conductivity. Heat can be conducted easily, thus ensuring that we have a uniform temperature all throughout. Mathematically speaking, we can classify systems as either lumped or distributed by the value of the BO number. If the BO number is relatively small, that is, BO number is less than 0.2, we classify the system as lumped. If it is 0.2 or larger, then that is already a distributed system. Okay? And our solutions for the lumped and distributed systems are different. Let's start with an example of a lumped system. A long copper wire, 0.635 centimeter in diameter, is exposed to an airstream at a temperature T of 310 Kelvin. The core temperature of the wire is increased from 280 to 297 Kelvin. If the surface conductance is 151 watts per square meter per Kelvin, determine how long would it take to achieve the temperature change. Here are the given of the problem. So we are given a long, thin cylinder with a diameter of 0.635 centimeters. The fluid temperature surrounding the cylinder is 310 Kelvin. The initial temperature of the cylinder is 280 Kelvin, while the final temperature is 297 Kelvin. The convective heat transfer coefficient is given as 151 watts per square meter per Kelvin. Now, for unsteady state problems, the first step that you have to do always is to solve for the BO number, because the BO number will tell us if the system is lumped or distributed. And as I have mentioned earlier, the solutions are different for lumped and distributed systems. Okay? We solve for the BO number. Definition, H times V over A over K. Let's first make a side calculation for the volume over area of this cylinder. The volume of a cylinder in terms of its diameter is pi over 4 d squared times L. And the lateral surface area of a cylinder is pi dl. From our calculations, pi would cancel, one of the diameters will cancel, and also L will cancel. That's why we were not given a value of the length, because it will not matter. Therefore, our volume over surface area ratio would be equal to d over 4. Now, you might be wondering, why did I only use the lateral surface area of the cylinder? We have mentioned in the problem that this is a long cylinder, so we are assuming here that the area on both ends of the cylinder are insignificant. Going back to the BO number, we now have HD over 4K, substituting 151 watts per square meter per Kelvin. Diameter, that is 0.00635 meters. I have converted it to meters so that we will all have standard SI units. All over 4 times the thermal conductivity of copper. So let's first look for the thermal conductivity data of copper in our handbook. It is in chapter 2 under transport properties. Okay, thermal conductivity temperature for metals. That is table 2-327. For copper, you see here that the thermal conductivity of copper is a function of temperature. And if you go back to our problem, you see that the temperature of copper varies from 280, which is its initial temperature, up to 297 Kelvin, or the final temperature. So for us to be thorough in our consideration of the temperature for the thermal conductivity, as well as for the other properties, we need to get the average temperature of copper. In this case, the average of 280 and 297 is 288.5 Kelvin. And you use that temperature in order to interpolate the value of the thermal conductivity of copper from the table. Going back, we can use the thermal conductivities of copper at 200 and 300 Kelvin and then just interpolate between. Okay? Interpolating, we find the value of the thermal conductivity of copper to be 384.7 watts per meter per Kelvin. We substitute this to our BO number equation. And if you take a look at the cancellation of units, Kelvin cancels, watts cancels, and meter at the numerator cancels with the meter at the denominator. Therefore, you are left with no units because BO number is a dimensionless number. Okay? Solving, we have 151 times 0.00635 divided by 4 times 384.7. The answer is 6.23 times 10 raised to negative 4. This is now our BO number. And since the BO number is less than 0.2, therefore we say that our system is lumped. Again, if we have a lumped system, that means that the temperature at any point of the substance for any given value of time would be the same. Okay? And since our system is lumped, we expect its temperature profile to be final temperature minus surrounding temperature over initial temperature minus surrounding temperature is equal to e raised to negative Biot number times Fourier number. If you'll remember, the Fourier number is defined as alpha times t over v over a quantity squared. And earlier, we have determined the ratio of v over a to be equal to d over 4. Substituting, we have alpha t over d over 4 quantity squared. Our Fourier number is 16 alpha t over d squared. If you substitute this Fourier number to our temperature profile, we have t minus t infinite over t sub 0 minus t infinity equals e raised to negative 16 Biot number alpha t over d squared. And then looking at this equation, we already have values for all of the parameters here except for the thermal diffusivity alpha. If you'll remember, alpha is defined as K over rho Cp. We now have the value of the thermal conductivity. However, we still have to look for the density and heat capacity of copper. So for that, we go back to our handbook. Let's start with the density. The density of metals is still found in Chapter 2. We have densities of miscellaneous materials, that is table 2-121. Let's go there. For copper, again, this is given as a function of temperature. If our average temperature is 288.5 Kelvin, that is between 250 and 300 Kelvin. So you have to interpolate between 8951 and 8930 kilograms per cubic meter. Okay? Interpolating, the density of copper is then 8472.83 kilograms per cubic meters. And then we do the same for the heat capacity. The heat capacity is found still in Chapter 2 under table 2-151. Let's look for copper. If you take a look at this entry for copper, the heat capacity is given as a function of temperature using this equation, 5.44 plus 0.001462 times T, wherein you simply substitute your temperature in Kelvin, and then this equation will give you the heat capacity in calories per mole per Kelvin. But we have to convert that to joules per kilogram per Kelvin to make it in standard SI units. Okay? So substituting and converting, the heat capacity of copper is 385.95 joules per kilogram per Kelvin. And with that, we can now substitute everything to our temperature profile in order for us to determine how long would it take to increase our temperature. Okay, let's substitute. That is final temperature 297 minus surrounding temperature 310. Initial temperature 280 minus 310. That is equal to e raised to negative 16 times the Biot number, 6.23 times 10 raised to negative 4 times alpha. Alpha is K over rho Cp, 384.7. Density, 8472.83. Cp, 385.95 times T. So time is our unknown. Let's represent that as X. And then divided by diameter squared, 0.00635 squared. Shift solve. Our answer is 29 seconds. We interpret this as it takes 29 seconds for our copper cylinder to heat up from 280 Kelvin to 397 Kelvin when exposed to a fluid having a temperature of 310 Kelvin. And since this is a lumped system, at time is equal to 29 seconds, our copper cylinder is expected to be 297 Kelvin all throughout, from the center to the surface, end to end, and to any other point in the cylinder. Okay, that's how lumped systems work. Let's move on. Next. A concrete cylinder, 0.1 meter in length and 0.1 meter in diameter, is initially at room temperature 292 Kelvin. It is suspended in a steam environment where water vapor at 373 Kelvin condenses on all surfaces with an effective film coefficient H of 8,500 watts per square meter per Kelvin. Determine the time required for the center of this stubby cylinder to reach 310 Kelvin. If the cylinder were sufficiently long so that it could be considered infinite, how long would it take? Okay, let me first list the given. Here are the given values for the problem. Now, before we can solve for the BO number, we need the value of the thermal conductivity of concrete. And based on table 2 and based from table 2-3 to 6, you can see there are several values for the thermal conductivity of concrete, okay? I'm going to use the value for cinder, which is 0.2 BTU per hour per feet per degrees Fahrenheit. We get 0.356 watts per meter per Kelvin. Okay, now let's solve for the BO number. Again, the BO number is H times V over A over K. Now, in this problem, since we are dealing with a short cylinder, we cannot assume that the top and bottom area are insignificant because in this case, the diameter is equal to the length of the cylinder. Therefore, all of the areas are important. So we have to rewrite our BO number expression to be HV over KA, wherein the volume of this type of cylinder is still pi over 4 d squared L, but then the area would be the total surface area of the cylinder, that is pi dl plus 2 times pi over 4 d squared. Therefore, our BO number is H times pi over 4 d squared L all over K times pi dl plus pi over 2 d squared. Substituting everything, we have 8,500 times pi divided by 4 times d squared L, 0.1 squared times 0.1 divided by K, 0.356 times pi dl, 0.1 times 0.1 plus pi divided by 2 times d squared, 0.1 squared. Our BO number is 466. Now, this is way greater than 0.2. Therefore, we say that this is a distributed system. For a distributed system, our approach is very different from that of the lumped system. Earlier, we simply used our temperature profile equation to solve for the time. Now, we have to use what we call Gurney-Lurie charts. This is an example of a Gurney-Lurie chart. No? So, the way on how we use this is first, on the y-axis, you have here what we call the unaccomplished temperature change. That is T minus T surroundings all over initial temperature minus T surroundings. On the x-axis, we have the Fourier number. That is alpha T all over x1 squared. Now, x1 in this case is the half thickness of your shape. So, if your shape is a cube, that is half of the side of the cube. If it's a cylinder, that is half of its diameter or the radius. If it's a sphere, it's the radius, and so on and so forth. For our case, we have a short cylinder. This is the representation of the short cylinder. Therefore, our x1 would be the radius of the cylinder. Now, if you will notice, we can solve for the x-axis because all of these parameters are given. But for the y-axis, we are not given the value of time. In fact, we're searching for the time. Therefore, we need to find the y value before we can solve for time. And for that, let's start by solving the x value here. We write that x is equal to the temperature at the center minus the surrounding temperature over initial temperature minus surrounding temperature. Substituting, 310 minus 373 over 292 minus 373. Our x is 0.78. Now, for this graphical methods, it would be very helpful if you can just retain one decimal place from your answer, 0.8 as our x. Now, going back to the Gurney-Lurie chart, if you take a look at the x-axis of this Gurney-Lurie chart, the subdivisions are not uniform. That means that the y-axis is at a logarithmic scale. The way on how we read this is that, let's say for example, you start here. This line is 0.1. The next line here is 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and then 1.0. Our value of x is 0.8, so we want this horizontal line here, okay? And then you look for your geometry. Our geometry is a short cylinder, which is this one. and then you look for the line representing that geometry. It is this diagonal line here. Now, what we want to do is you look for the intersection between this diagonal line and the line representing x is equal to 0.8. So 0.8 here, and then intersecting with the diagonal line, we have this point here. This point here, you simply have to read the y value of this point. Take a look at this point, and then read from below. The y value is this one. We say that our y value is 0.1. Okay, again, you look for your x value. In our case, that is 0.8. You look for its intersection with the diagonal line of the geometry, short cylinder. This is its diagonal line. Its intersection leads somewhere here, and the y value of that is 0.1. Okay, so we now know that our y is 0.1, and y is equal to alpha t over radius squared. The only thing remaining for us to do is to look for the thermal diffusivity of concrete, and then we can now solve for time. Now, in your exams, you have to look for the values of the thermal conductivity, density, and heat capacity of concrete. But for illustration purpose in this example, we have a value of alpha, and that is 5.95 times 10 raised to negative 7 square meter per second. So if you substitute everything to our equation of y, we can now solve for the time. That is 0.1 times radius squared, 0.05 squared, divided by the thermal diffusivity, 5.95 times 10 raised to negative 7. Now, this answer is in seconds. So our answer is 420 seconds. Let's convert that to minutes. That is 7 minutes. How do we interpret this? We interpret this as it takes 7 minutes for the center of our cylinder to reach 310 Kelvin if it is exposed to a surrounding temperature of 373 Kelvin. Okay? And since this is a distributed system, we expect that the different points of the cylinder would have different temperatures as well. For instance, we expect the surface of the cylinder to be around 373 Kelvin in temperature at around 7 minutes in time because it's the first surface exposed to the hot environment. That is how distributed systems work. We solve them using the Gurney-Lurie charts. For the second part of the problem, we are required to determine the center temperature of the cylinder if it is an infinitely long cylinder, meaning it's no longer stubby like this cylinder here. So if we will be considering infinitely long cylinders, all of the parameters given here would still be the same. What will change is the diagonal line that we are going to use for the geometry in the Gurney-Lurie chart. So the value of x will still be the same, however the value of y will change. If we take a look at the Gurney-Lurie chart, this is for short cylinders. This was our previous system. But now for the second part of the question, we have an infinitely long cylinder. This is the curve for the infinitely long cylinder. Okay? If we take a look at the intersection between x is equal to 0.8 and this curve, it intersects somewhere here. The value of y as seen from the intersection is slightly greater than 0.1. So let's have that as 0.125. If y is 0.125, let's solve again for the time needed. That is 0.125 times 0.05 squared divided by the thermal diffusivity, 5.95 times 10 raised to negative 7. Our time for the long cylinder is 525 seconds, or in terms of minutes, that is 8.75 minutes. What we see here is that it takes longer for the long cylinder to reach the proper temperature at the center than for the short cylinder. The reason for that is, for the short cylinder, you have the lateral surface area plus the top and bottom areas for heat transfer, while for the long cylinder, most of the heat transfer occurs on the lateral surface area only. That's why it takes longer to raise its center temperature. That's how we use Gurney-Lurie charts for distributed systems. In this example, we were only concerned with the temperature at the center of the shape. However, for some instances, it is also useful for us to consider temperatures that are not at the center of the geometry. Okay? For those instances, we will be using different Gurney-Lurie charts, and we will be introducing two more variables, letter M and letter N. Okay? Those will be highlighted in an example in a separate video. But for now, you have to develop your skill of reading the Gurney-Lurie charts. Let's proceed. Last example. Soil having a thermal diffusivity of 5.16 times 10 raised to negative 7 square meter per second has its surface temperature suddenly raised and maintained at 1100 Kelvin from its initial value of 280 Kelvin. Determine the temperature at a depth of 0.25 meters after a period of 5 hours has elapsed at this surface condition. This is an example of a semi-infinite surface wherein heat is only introduced on one side of your geometry. If you will compare this, in the previous examples, the heating fluid is actually all over our shape. This time, only the face of the soil is being heated, and we are treating the entire depth of the soil as a semi-infinite surface. For semi-infinite surfaces, we use this equation. We have the same unaccomplished temperature change, but now on the right-hand side of the equation, we have what we call the error function. I will demonstrate how to use this error function later. But if you take a look at the contents of the error function, you have x over 2 times square root of alpha times t. X here corresponds to the depth at which we measure the temperature, alpha is still the thermal conductivity, and t is the time elapsed. Okay, let me first write the given to this problem. Here are the given to the problem. We have here our soil surface, of which its temperature was raised to 1100 Kelvin. The initial temperature of the soil was uniform at 280 Kelvin, and we want to determine what will be the temperature at a depth of 0.25 meters after 5 hours of exposure to this high temperature. You're given the thermal diffusivity of soil, that is 5.16 times 10 raised to negative 7, and we have here our equation for semi-infinite surfaces. Now, the first thing that we have to do here is to solve for the contents of the error function. You see here that the error function contains the collection of terms x over 2 times square root of alpha t. So let's solve for that first. X, representing the depth, is 0.25 meters, divided by 2 times the square root of alpha, 5.16 times 10 raised to negative 7, times 5 hours, convert that to seconds, multiply by 3,600. This is our answer. The collection of the terms inside of the error function is 1.3. So we write surface temperature 11 minus T, which is our unknown, divided by surface temperature minus initial temperature is equal to the error function of 1.3. Now we have to take a look at an error function table in order to determine what is the error function of 1.3. I have here an error function table. Okay, these are the values of phi, or the terms inside of the error function, and this is the value of the error function. Okay, since the value of our phi is 1.3, we find that the error function of 1.3 is 0.9340. We can now use that in our calculations. Okay, so this is equal to 0.9340. And with that, we can now solve for the temperature. That is 1,100. I am now rearranging the equation. Minus 0.9340 times 1,100 minus 280. Our answer is 334.12 Kelvin. Okay? That is how we treat semi-infinite surfaces. I will be giving you more solutions to problems in the upcoming videos. Okay? That's the end of this lesson. I hope you have learned something. If you have any questions, do not hesitate to ask me. And as always, keep safe.